Hey guys, we're ready to continue on with the next presentation. So I'd like to introduce Andrew Toff, the Product Design Account Manager with Pharaoh, and he's going to be presenting some laser scanning technology with myself.
Hi, thanks Mike. Hi guys, Andrew Toff here from Pharaoh Technologies. Like Mike said, I'm the account manager for product design applications for Pharaoh. I've been spending most of my time for the past 5 years up in the northeast, up in Pennsylvania, doing some metrology work. So using some of the products that Pharaoh makes to do 3D measurement, quality control, and some reverse engineering. At this point, I've joined a group within Pharaoh that does product design as a whole. So here, let's see what we got here. Focusing mainly on reverse engineering projects, scanning to print, scanning to CAD, and in this case, we worked on a little bit of a project together last week here at TPM, where we were able to capture some of our design inspiration to build on and not necessarily have to remake the wheel on a project that had a fairly complex little shape to it. So this right here is a 3D print of what would be the flight stick for a F4 Phantom and also some of the Hueys back in the day. Actually, this thing made its way into quite a few aircraft in American history. So at any rate, I wanted to just talk just for a minute about what Pharaoh does and who we are, if you guys haven't heard of us. Pharaoh's been around for about 35 years now, and we make 3D measurement systems, typically doing those things for quality control, for efficiency gains, for time savings in manufacturing, and the side projects, the fun things, if you will, that I've gotten to be part of focus around making new products, adding innovative features into existing products, doing aftermarket work, improving the performance of legacy parts. And where you can't remake things, or where you can't source them rather from the original manufacturers, being able to scan those and remake them. Now when we get into some of these things, where Pharaoh's been across the world now, we've got a little over 20,000 installs worldwide. We've been around again for 35 years at this point. We're based in Lake Mary, Florida. So we make these Pharaoh arms. I'm not sure you can see this off to the side here. This is a Pharaoh Edge HD scan arm. We also make something called the Design Scan Arm, which is very similar. And so this has been kind of our bread and butter product over the past 35 years. This is where we started, was this articulated portable CMM. So let me just move on here and talk about what Pharaoh's goal is now. As we've evolved and we're touching so many different markets, we've got a wide range of products, not just the Pharaoh arm, but 8 or 9 other pieces of hardware. We have the Pharaoh arm, we've got the laser trackers, we have focused 3D scanners, so that's a laser scanner, one where you put it on a tripod. It's able to rotate around and scan 1 million points a second, plus or minus a millimeter now from up to 350 meters away, and that's the radius of the scan. So yesterday I was scanning a helicopter inside and out, an old design that they were going to do some revamp work on using that focus. Today I want to show you and focus a little bit more here on the arm, but the arm, the focus scanner, we've got something called the Freestyle, which is a handheld scanner that captures both color and points. We've got the Pharaoh gauge, we've got the cobalt array imager, and that's something you can mount even on a robot in a factory to take structured light scans very quickly. They actually process data on board all by themselves, so we could put 10, 20, 30 of those in an array and capture a pretty big volume. At any rate, a pretty wide range of products from us, but our vision here is to be known as the world's most trusted source for 3D measurement, imaging, and realization technology. Our mission is really to enable mankind to easily and accurately connect what's the physical world with the virtual or digital world. All right, so really quick, when we're talking about this product design vertical that my team is taking on, we've done historically side projects and small percentage of our business a little bit outside of just the manufacturing and the quality control realm. And now we're focusing a lot heavier on that because it's such a great emerging market. There's so many different types of printers out there and 3D CAD integration that it makes sense to step in and go, hey, we would like to help more and more people be able to approach this type of industry be able to scan and digitize, and we're the pros at it when it comes down to precision and accuracy and density and being able to see details such as your fingerprints in a 3D laser scan as opposed to having little blocky polygons. So what we're looking to do here is copy, scale, reproduce parts, develop CAD models from scans or from a combination of scans and concepts, documenting design intent. So being able to capture something that might be worn out and be able to rebuild it and fix it. Where I like to think that the future really lies is providing that front-end input. You guys are SolidWorks users. You know what you're doing in 3D modeling, right? It would be nice to be able to speed that along, get you a little closer to what your concept is in mind or what your design inspiration might be in mind, and then get that into CAD quickly. So I'm going to show you a little bit of that. Digital archiving, that's another one too that we don't talk about that much, but being able to capture something, save it, so that later we can refer to that. We don't have to keep something around or store it, we just want to capture it quickly. All right, so here's the design scan arm. This thing is a 7-axis portable articulating CMM. Has both contact measurement using probes, and we have a wide variety of those, and a laser scanner on it. So what's happening is that this arm here is tracking 7 axes of rotation, and it knows where it's pointing, and it knows where that laser scanner is. So you wind up getting the ability to capture 500,000 points a second, a little bit more than that actually, and map a surface quickly, turn it into surfaces in CAD, right? Okay, so there's a quick scan of fingerprints. Let me go back one here. Talking about some of our partners and how they interface with your SolidWorks software, right? 3D Systems Geomagic software. We've got 3 different basic programs that we would use in there to be able to scan directly into that program using the arm and then affect some type of a mesh or model or sketches or all 3 of those things. So Geomagic Wrap, scan it, mesh it, send it over as an auto-generated surface like an IGES surface or a step surface to CAD. DesignX, that's where you can scan something and turn it into a parametric model, right? We got surface modeling, solid modeling, mesh, STL modeling, and you just live transfer that out. So it keeps a history tree, it's parametric, and it feeds itself right back into SolidWorks as well as Inventor and a number of others, right? And then we got Geomagic for SolidWorks, which is a plugin directly into SolidWorks program. You take a few less points, and it's able to crunch that directly. You can sketch right into SolidWorks, so that's pretty exciting. It's a new piece of software from 3D Systems Geomagic. All right, here's a basic workflow, right? If I'm walking into a company in Pennsylvania, let's say, outside the Philly area, this is apart from a company that I've done work with called Shredder. They make valve bodies, right? So they gave me this casting, we scan it. This scan took about 20 seconds, right? Capture several million points, and we're able to scan and then have the software, as it's intelligent, look at where the curvature changes, turns it into easily selectable regions, and you can pop out some solid features. If that's all you need, just send that out to SolidWorks. If you want to go a little bit further and actually create sketches, parametric sketches, then you cut the sections into it, you create those sketches, you revolve them, and you boolean together your model. So you can pop out your solid features. There's a lot of wizards and tools in there. I'm going to show you a couple of those in just a second. And then you do a design validation step. So I might switch out of this PowerPoint mode for just a moment, and let me pull open this Geomagic DesignX program. All right, I'm going to show my screen, I believe. Here we go. All right, great. So what I've got here in front of me on the table is this is a part. I can't remember if this was the Mustang one or if this is the one from the Corvette, but it's a thermostat housing, right? It's an aluminum casting that's got some features to it. It's got some things I might want to probe these and get the holes from it. But in order to quickly scan this and get a model out to show you guys, I'd like to just kind of dive right in and say, hey, I'm going to connect to my Pharaoh arm by clicking the live scan button, right? And then herein, here we go. I want to show you that we can probe some surfaces, right? I'm going to probe the mating face where this would connect to that aluminum V8 engine in either one of those 2 cars, right? Pull the arm down. We're going to make contact with the surface here. I pull the trigger. It takes the point. It knows where these points are relative to each other because the encoders are reading where that is. So there's one. I'm going to go and probe the table here too, so you guys can see a couple of different features coming in. right? So I got a couple of planes. We make contact. We could also probe circles, and we can probe slots, and we can probe freeform surfaces, right? There's a number of things that we can do. I want to show you really quick. When we pop out of this mode, you've got these things, these faces, in the orientation that they were in. Now I'm going to do a couple of scans. I'm just going to do a couple of quick scan passes so that my processing time is cut down to just a minute or two. But know that we can dwell on this. I turn my resolution down to about 1/10 of what we can capture just to speed up the process, because I got about 5 minutes to show this to you guys. So take a look. I'm aiming this scanner. Oh, backtrack just a second. I'm aiming this scanner at the part. There's a laser scanner mode. There we go. What I've got is blue laser line right here. I don't know if you can see it on my hand or on the table on the part here, right? This blue laser line, we're using blue laser. We've got an extremely fast camera capturing 280 frames a second, which allows us to reflect off surfaces but not cause a lot of noise, right? It's pretty unique. It's a nice way to do that. And all I do is I'm aiming it at the part. As you can see, the screen is going to change direction, right? As I'm pointing in a different area. See how that rotates? So I'm just going to pull the trigger here, right, and do a quick scan pass. There you go. I captured that part, captured most of that part. I'm going to point it on the other side in case I got a shadow here. So 3 quick little passes, and that might be all I need. I'm going to focus a little bit on the hole in there, right? Just a second. I got my internal safety sensor going off. Saying, hey, I bent that arm a little too far. A little stress on it. Might get a little bit less accuracy that way, so it flagged me. All right, I say okay. Here we go. I've got that quick scan. You can see how those faces are in place relative to the other faces. I can scan the other side. In this program, you don't necessarily have to get this watertight. You only need a partial amount of data in order to get a solid model out. So what we've got is multiple scan passes. I can get the accuracy on the arm are probably about 0.02 of an inch. And so I'm just going to let these shake that last couple thousandths of an inch out. Basically, I'm going to let each one of those scan passes float relative to each other, just slightly. And this is just the benefit of having that encoder-based scan system, right, in the arm. There we go. We've got the nice little mesh showing, right? There's probably a couple million points there. We probably don't need all that much data, but here in polygons, right? So each one of these is a point. They show up as a mesh, and I'm just going to join those 4 different times I pulled the trigger, those 4 different individual scan passes together, merge those into a model here, and now I got a little STL model. If I had scanned the other side, we could probably just go ahead and print that if that's all we needed. But in this case, I actually want to create a model from it. So like on that previous scan, we've got my little auto segment here. I'm going to decide what sensitivity, how many different regions I want to break it into. It takes just a minute. Right? Each one of these little regions is colorized now. I don't know if you guys can see that in color. If I wanted to take maybe this section right here and say, I would really like to create a sketch on that, and I'd like to create a model. There's a lot of tools in here. This is one called the Revolution Wizard. And Revolution like revolve as opposed to a group of people in an uprising. So here we go, Revolution Wizard right here. And I'm just going to let that go ahead and extract and figure out what that segment of the model should look like. And it does so by cutting a little bit of a sketch through those points and then revolving it. So here we go. We've got that segment of the model done there. There it is. It's got a little bit of the flange there. We can actually dive in and take a look at how we did on our sketching relative to what our scan was. So a little design validation right there as well. So in this, just kind of a basic tool, I can push and pull and change that and take a look at how we've done as far as the scan to model process is concerned. So there's a little bit of a revolve, right? You guys see that? Next thing I want to take a quick look at is maybe this flange right here. We want to create a sketch. Say I'm going to create a mesh sketch. So I grab that face, and we can pull right through here. Again, just partial data, but looking at the face itself, right? I'm going to do just a part of this, just to be quick here. But if I tell it to go ahead and create that sketch automatically, just based on what its guess is, it does a pretty good job of it. And I might even just take and pull a couple of these little features out. But if this is my project, if this is the set of features that I want to do, I'm I'll check here. I'm just going to go ahead and block this in, but I could grab the back side of that flange as well. But for right now, I'm going to go ahead and connect it all up. Right, just to kind of mock it up to show you what this looks like. You create that sketch, then you can then extrude it, pull it up. Right, you can pull it up any nominal distance. We can make it higher or lower, or we can actually show this mesh here and go up to a certain point with it. So up to region, right, or line, either way. So let me do that one more time here. Your extrusion, there it is. You go towards the table with it, and just show you there's a solid, popping out of that. So we could trim this, and we could do this as a revolve as well. We could pull out some basic features. So if that's a sphere right there, we'll just call it such, and you've got your basic information. If that's enough for you, if that's enough for you to jump into SolidWorks now and get started, then we'll just live transfer that into SolidWorks. Right, we grab our first features. We'll say, hey, we're going to go ahead and put that across, pop into SolidWorks. Okay. Just wanted to show you how quick it is to get from a quick scan to a model. Right, trying to fit everything into view here. Whoa. There we go. So that just comes in as CAD. Now we can edit that. The sketches are parametric. All right, let me jump back over and just cover a couple more slides and show you some interesting things for about 3-4 more minutes, if that's okay. You guys swap me over? Thanks, guys. All right, great. Cool. So that was that process, right? We scanned, meshed, created a couple of regions so we could easily pick some things, right? Did a little sketch, although if I had scanned a little bit more around that, we would have had a full sketch, right, of that one piece. Here's some things, even like that was a pretty basic part, pretty, prismatic, if you will, pretty easy to make. What if you get something complex, right? This is a face. It's a mannequin that I scanned at Bressler Group there in Philadelphia, where they were doing some design for Rydell football helmets. And so we scanned this in, and we're able to do something called auto surfacing. So we know within a couple thousandths of an inch that each one of these patches that you see on the right side defines that surface, right? We can just fire that right over to SolidWorks. They can sketch on it. They can virtually assemble some things on there. Here's my friend Chris. I scanned Chris's face. That was about a 5-second scan, 1, 2, 3, 4 passes. And we were able, he's got a little 3D print of that I made that I was making fun of him with just a little bit, but wore his face for Halloween. All right, here we're virtually assembling Chris's face on a mannequin in case we were building a crash test dummy or a robot, right? I wanted to talk to you a little bit about what other things we might be able to do. Here's where we're trying to take this project that we did, TPM, have some design inspiration. We're thinking about, hey, how do we convert some of these things that we love, some of these really complex shapes that, timeless designs, how do we use those and leverage the brilliance of some of these designs to make something new, to make something else that's impactful. So we're able to take this idea, scan the B8 grip there, and then change it a little bit, do some work with that. So we scanned it in, there's the raw scan on the right. We're able to pull some of the old buttons and things off of there and smooth them and talk about some of the things we want to do to make this accessible, make it usable by somebody, a young child. In that case, you might be a person with a disability or have some mobility issues, able to jump in and use this control, have a little bit of inspiration there. All right. We took a couple of buttons off of that, some of these old 1950s and 16s buttons, and we scanned something that the newer generation might have a little bit more familiarity with and know inherently how to use it, just making it easier on a daily basis. Scan a few of the buttons to that end, right? Just like I showed you before, we scanned it, we regioned it, pulled a couple of buttons, I made a revolve there, and Mr. Staples here did the rest. So we popped out, did some extrusions, just like I showed you on the flange for this little part, right? But then I got that complex shape. Do I want to divide that up into 100 different sketches? No, I don't really need to. I want to be able to cut some sketches and maybe some profiles and merge things in SolidWorks where I know how to model a little bit more. So I just said right click, hey, make this a surface model, auto surface it, and then we transferred it over to SolidWorks. Probably about a 5-minute process there. All right, so let me go ahead and hand it over, and I think Mike's going to tell you a little bit more about what he did once they got into SolidWorks. Thanks for your time, guys. Look forward to any questions later.
Great, thanks, Andrew. All right, so this was a really, really fun project. Definitely enjoyed working with Andrew on this. He was able to get us some amazing data to get started with, and what I'd like to do now is just kind of share a little bit of that process with you from an engineering standpoint, taking that scanned data. We'll walk you through a couple of steps here. The inspired design aspect of things. So Andrew touched on that a little bit, and I'll kind of carry that a little bit further, as well as the development. You know, once we get into SolidWorks, how do we then go and take this design and really kind of bring it to life? And then once we've got the data in SolidWorks, you know, what's going to happen next? You know, there's some additional stages that need to happen to really make this product manufacturable. So again, this was a pretty fun case study that we put together here. So I'm going to start with the design aspect. So as Andrew mentioned, you know, we wanted to leverage some existing ergonomic design. So what does that really mean? Well, with a background in power tool design, you know, I know firsthand that it's extremely difficult to 3D model something that's really going to be comfortable. That's a long iterative process to be able to go ahead and print things out over and over and test things out, make sure that they're comfortable, you know, size things for different hands. So really in this example, what we wanted to do is say, you know what, we have some ergonomic designs that are already known, industry proven, they're already comfortable. So we wanted to repurpose and leverage the data from a gaming controller and from a flight stick. So what were some of the goals that we wanted to achieve with this particular design project? Well, first up, we wanted to ensure comfort for the user. You know, thinking about the target audience, you know, this isn't somebody in a fighter jet anymore. This is going to be somebody using maybe an extreme wheelchair, for example. So maybe using it for many hours a day. So comfort was really important to us. So how did we address that? Well, in this design, we decided to go ahead and add a rubber grip. And again, we wanted to leverage some proven ergonomic designs from both gaming and from the existing flight stick that we knew were going to be comfortable. We didn't have to go through a ton of different iterations on the front end to try to figure out what size this should be and how it was going to be comfortable. So the next goal that we had was we wanted this to be a fun project, and we wanted some of these controls to be familiar. So again, that's why we jumped and decided to use some gaming controls and just physically took apart Xbox controller, did some scanning, and brought that data in. And then finally, we knew that safety would be important. Whenever you have children involved, certainly safety is a huge concern to everyone. So some of the ideas that we came up with were to add in a heart rate monitor as well as a call button. And kind of also within the design scope, we decided to remove the side button off of there to give the user a little better grip. So again, we're thinking of some extreme situations that this product could be used in, and some ways to make it safer and modify the design in a really kind of an inspiring, innovative way. So let's talk a little bit about the development of how we went about going through this process. So as Andrew mentioned, we used the scanner to scan the data directly into a CAD application. So you can see there a real scan with millions of data points, and we were then able to leverage that data. There's a few processes that you can do to kind of work with that data. You can simplify it, you can tighten up any holes that might be in there, and really give yourself some unique surfaces and faces wherever the curvature is changing. Let the software kind of identify those different regions so that you can then turn that into usable CAD data. You know, really it was a cool process that we went through. So knowing that this was going to be used for children, we did a little bit of research, and 80% seemed to be a good scale factor. So we're taking this, you know, full-size flight stick, we're scaling it down in CAD. That's one simple feature in SolidWorks. It takes 2 seconds to do. Next, we wanted to go ahead and model some of the different features. So going through that workflow, you can model standard features that are very simple, like the buttons and the revolve feature, like we have shown on screen. You can model complex geometry. You can have it automatically grab some of those curved surfaces and regenerate those complex surface bodies. So whether it's simple or complex design information, you can capture that immediately in your CAD package and regenerate it. We identified that there were some regions that we didn't want to have. So off to the side, we just wanted to completely remove that button. In SolidWorks, when we're working with solid bodies or surface bodies, just by simply deleting a face or a group of faces, we can actually remove that geometry. It turns it into a surface body if you started with a solid. In this case, we did. And then once we remove that, we just patched in the hole, and now we're thickening and we're back to a solid body. So very simple and straightforward in SolidWorks to remove that geometry and continue to work with solid features. And then adding new geometry. So I mentioned that we wanted to add in that heart rate monitor. We also wanted to add in that rubber grip. So these are familiar capabilities within SolidWorks that are very simple and easy to model, very easy to leverage existing ergonomic surfaces and be able to offset those surfaces and then generate rubber grips that are going to be offset at the exact distance, separate solid bodies. And so, again, anywhere that we needed to remove or add geometry, those are very simple stages that we were able to do in SolidWorks. And then the final, once we have a basic design that we think is going to be really good and comfortable, of course, just like any other product design, you still need to go through the rapid prototyping stage. You need to have something that you can hold in your hand. So here we have the original design, and then here we have the printed out smaller version that we generated. And to be able to print this thing out and hold it in your hand and get an idea of the comfort of this is really just an incredible benefit. Again, with a power tool design background, I know that without rapid prototyping, that's impossible to perform that type of design. So to be able to hold it in your hand, get an idea, grab your target audience, get a focus group going, let them start grabbing it and making adjustments, letting you know what areas are comfortable, what areas aren't. You can physically mark up right on the prototypes, go back to SolidWorks, make some design changes, and then reprint your prototypes. And within just a few hours, you've got in your hand the next version of your design that you can then go ahead and show to the focus group again. So that's kind of the process that we went through to develop this design. And so next I'm going to touch on, from here, where would we go with this design? So we've got the main solid model, but that's really not the end of the story, right? There's some manufacturing features that need to be included. And, for folks that are familiar with SolidWorks, you guys probably know some of these features, but for those that aren't, these are integrated tools right in your design environment that allow you to do things very specific to plastic part design. It's included with all versions of SolidWorks. You're able to shell models. You're able to split things up into multiple bodies. If you had a two-half mold that needs to come together, you can split it into two different solid bodies. There's integrated tools that walk you through a step-by-step wizard to create lip and groove features. And then internal to plastic part design, you may have some mounting bosses, supporting ribs, any other types of features, maybe some snap features that allow you to snap two halves of a design together. So there's a variety of tools from a plastic part design aspect that are integrated in SolidWorks that would be kind of the next step. And then once the finished product is fully designed, some additional stages would be the mold design. So with the mold design, we can analyze draft and ensure that we have the proper amount of draft. We can add draft wherever it's needed to ensure that the part is going to be able to come off of the mold. We can scale easily to accommodate for shrinkage. There's several other tools that are included. You can do parting surfaces and parting lines. You can automatically, utilizing the mold tools, again, that are included in all versions, utilize the mold tools to have it automatically separated into two mold halves that have the full geometry. So a pretty slick workflow that really allows you to go to the full design of your finished mold in SolidWorks. And then if you have complex designs, maybe you have some side cores or some core pins that you need to include with your mold design. All that stuff is available, again, directly in SolidWorks. So those are some of the manufacturing features. And then for the fun stuff. So once we know that it's manufacturable, once we have all that stuff designed, well, we're still in a virtual environment, so we're able to go ahead and run some validation and ensure that the design is going to be strong enough. That would be another next step. Some additional steps would be maybe the electrical design, some of the circuit boards and integrating those and ensuring those are going to fit properly and perform all the capabilities that we need with the button on the bottom and the controls on top. Creating high-end photorealistic marketing content. So, you know, it's a great way to leverage your CAD data, like we mentioned in an earlier presentation, to be able to create stuff that you can go ahead and post on your website. You can go ahead and show at a trade show. You can see the little animation showing in the bottom that was done in SolidWorks Visualize. And then, of course, your technical communication. So teaching somebody how to use this product in a virtual environment is a great application for technical communications. You can actually integrate, interact with the software, hit some buttons, and see how things function. Have a version of the product right next to it, so as the user hits those controls, you can see the product actually moving and train the user how to use this product before they ever get into a real-life situation. So imagine teaching somebody how to fly a drone, for example. You know, that could be pretty complex, some unfamiliar controls. Well, if they can practice in a virtual environment, less chance of destroying a real product, or in this case, we had some safety concerns. So technical communications are an important aspect that, again, we can leverage our CAD data to be able to perform. So just a real quick summary. I wanted to touch on a couple of points here. With this amazing design project that we went through, we had a lot of fun with it, and what we wanted to be able to showcase for you guys is that leveraging this scanning technology, we're able to accurately capture with a lot of control, accurately capture both simple and complex geometry. We were also able to model ergonomic designs. Again, there's some challenges with ergonomics and having to model things in a 3D environment and not really be able to touch it and feel how comfortable that's going to be. So we addressed some of those concerns to be able to model with confidence. And then finally, being able to precisely locate components. You know, with the accuracy of this scanner, it's just incredible. So we were able to get true 100% accurate data so that we could locate the buttons and locate where we need all the different controls and ensure everything lines up and fits right the first time. So with that, thank you for your attention, everyone, and we're going to kind of pause for just a moment here, check and see if there's any questions, and we'll be right back. No questions? We do have questions. Okay. Come on up here, Andrew. We'll have Andrew join us, and we'll address a few questions. See if you can pull those up for us.
Hi again, guys. I know one of the questions that was asked was if I could talk a little bit about the Pharaoh Cobalt scanner. So yeah, I'd be happy to do that. We've got several different devices, like you said, that Pharaoh produces that fall into this category. We can use them for product design. We can scan. On this project in particular, the Cobalt would have been a pretty good alternative to an ARM. So essentially, the Cobalt is it's a structured light imager, and what it does is it basically emits a fringe pattern of structured light and has stereo cameras that allow it to focus down on an area. The accuracy, right, when we're talking about repeatability of a device like this, is one where you've got right around 1,000th of an inch, right? So you set up this imager. It can go on a robot, it can go on an array of these things, but you set it up and point it generally at an object, and you either move the object or you move the imager. You can move the object on a turntable, you could move the imager on a tripod and set it down, you can put it on a rail or a slide or a rotation of some sort. But the idea is we've got this unit, this imager unit that takes up to 9 million points in a single flash. Right? It goes flash, flash, there you go, you got 9 million data points. You can take that, it processes that data on board and then feeds it in. The unique thing about the Cobalt that you're asking about is that you can actually put multiple units together. We could put 10 units, and we did at the IMTS trade show, we took 5 or 6 of these and we put them together and we showed how unifying where they are relative to each other, going, hey, these are all focusing on the same thing. We're able to flash with each one of those units and cover a much bigger area in order to create a pretty dense point cloud. I don't know if you can share my screen real quick.
Yeah, we can switch
and I can show you an example. actually have it on my desktop right now. Show an example of something that we scanned from a product design standpoint with the Cobalt 9MP, which is our latest launch of that unit. I'm going to click on Show My Screen, and I'm going to hide everything on my desktop, and then there on my desktop background, which is hiding over to the right a bit. So we got, I'll just open up my shoe picture here. This was one of my applications engineer's shoe, actually. So this is just a running shoe. It's probably like a size 4.5 or 5 Melinda shoe. And we wanted to see what kind of resolution we're getting out of this new launch that they handed us the day before the trade show. And it was pretty phenomenal. So shooting just the bottom of the shoe, you see every little piece of tread there. I can see how much wear has been, on the ball of her foot. We can kind of categorize who she is. From a forensic standpoint, they might take a shoe impression, right? Or they might take a footprint and compare it to someone's shoe and do a color map overlay and go, hey, it was clearly this person and this is how they drag their heel. But in this case, what we might do from a product design standpoint is take this great architecture, take this great design of the shoe here, and then maybe modify that a little bit to show a hypothetical, what would next year's shoe model look like? What if we changed the pattern here, but we kept the basic dynamic shape the same? How would we edit our tooling, right? Downstream in SolidWorks, you go, how do we edit our tooling to get this new, concept that we've got for a tread pattern? And so this is just a quick example of within Geomagic Design X or Geomagic Wrap, what that Cobalt data looks like. It's pretty sweet. The benefit of having that is that it can be an automated process. You can go, hey, I want you to take 10 images and just rotate it, 36 degrees per image on the turntable. Whereas the ARM itself has a lot of flexibility, and if it's one-offs and it's something where you've got a lot of line-of-sight concerns, things where you want to articulate it and catch data, an ARM kind of fits better there. So one of a few different technology types that we have on that.
Awesome.
Any other questions?
Yes, so that ties right into the next question, actually.
Sure.
The intellectual property. Are there any concerns with scanning physical products, kind of bringing that in and repurposing design information from other intellectual property?
Yeah, to a certain degree, you've got to be careful with what you actually are scanning. And if you're trying to put out a brand new product, you say, hey, we've got this great new design, be careful not to step on the legal intellectual property toes of anyone who might want to sue you over that. The bottom line is there's an awful lot of different types of design out there, and there's different types of reverse engineering as well. If it's about analyzing something and creating a new design, if it's about, like we did, we took some design inspiration from a very old design for the aircraft flight stick, and we distilled it down, we modified it, we modeled it, we refined it quite a bit. We did a number of things that were careful. The thing that we scanned, that Xbox controller, was actually an aftermarket, one of the slightly less expensive aftermarket Xbox controllers, and so that had already kind of been refined before. It's a pretty universal platform. That said, before I would go to market with something or borrow money from anyone to do so, I would definitely check with an intellectual property lawyer on those things. But there sure are a lot of aftermarket parts out there in automotive, sure are in a number of other areas as well. So I wouldn't let that be a big stopping factor for whether or not you wanted to pursue that type of technology.
Great. One more question. So the other question is in regard to taking a physical model and comparing that with the virtual CAD data that was originally designed. So how can you bring it into the software? How does that work to be able to compare that with the virtual CAD data?
Yeah, it's pretty direct, to be honest. If it's a matter of color mapping, let's say this print that we made, right? This could be the part that we had a supplier produce for us. When we get it in, we're going, okay, this looks a lot like our design, but let's go ahead and overlay it to our CAD model. Geomagic makes a really nice software called Control-X. And basically what you do is you right-click, you say, hey, I want to import the CAD model, and then you say, I'm going to scan the part, and you have it best fit or overlay. Or you can actually touch off on certain features or datums and say, hey, these datums on my model should match these things that I'm probing or touching or extracting on my part. And so you can align it based on a certain type of feature. I've done an awful lot of that. That's where I came from Pharaoh. 5.5 years in Pennsylvania doing a lot of castings, a lot of automotive parts, aerospace parts. And so that's really where Pharaoh grew up. That's where we spend most of our time for the past 35 years, is in metrology, in comparing usually CAD models to parts that we're probing, or scanning. You also may have times where you don't have CAD, quite often actually. And then what you do is you scan the thing and you slice it up and you take the virtual caliper tools and you take and extract features to match your print and do a quick comparison that way. GD&T is a possibility, different alignments are possibilities, but that's really kind of where our wheelhouse has been. In talking about product design, you really can't avoid that because validating those designs and making sure that you're getting good quality out. That's just one more software package. I think they'll even give you a discount if you buy both the design software and the inspection software, but certainly something that we can address. If you want to shoot us a message, I'll be happy to talk to you one-on-one about that. Maybe there's something in particular that you guys want to take a look at. Thanks.
Awesome. Yeah, thank you, Andrew. Yeah, definitely the GD&T is a big concern for designers and being able to measure, like in the question they asked about like perpendicularity and the location of holes and things like that.
Yeah,
so,
absolutely. So that's where we've done most of our work in the past 35 years. So certainly something that we can address later.
Great. Thank you, Andrew.
Thanks a lot. I appreciate your time.